Okay. So if f was continuous here, then you would be sure to have correspondence at every single point. But we only really need f is L2 in order to at least make these formulas work, and they'll apply essentially almost everywhere on x's from minus L to L. Okay. All right. So what are we doing, right? We want to find essentially how to pick an and bn for a particular f that we have here. Okay. And so the way that we'll do that, right, is we'll integrate, first of all, f of x dx in order to get our formula for a0, okay? So when I just integrate f of x, because of the oddness of sign, and then also the fact that the area above and below for cosine also cancels out, then essentially these integrals all are going to evaluate to 0, right? So this basically integrates to 0. This integrates to 0. And we're just left with 2LA0, which implies that A0 is equal to 1 over 2L integral from minus L up to L of f of x dx. Okay, so that's great. The question is now, how do we get all the other coefficients? Okay, well, in order to get the other coefficients, right, we can exploit the fact that sine is going to be orthogonal to other signs of different frequency, okay? So if I integrate f now against sine of m pi x, right, where m is some integer, right, or natural number, I guess, in this case, some positive integer, right, then because of the orthogonality of signs, right, first of all, the a0 part, m pi x over L dx, this is going to integrate to 0, okay? This infinite sum now cosine and sine are always orthogonal to each other, okay? So this is going to integrate to 0. And then this term here, right? I'll write this as a separate sum, bn integral from minus L to L of sine of n pi x over L, sine of m pi x over L dx. These are going to be orthogonal to one another, basically unless m equals n in this case, okay? So basically when m not equal to n, the integral is equal to 0, okay? And when m is equal to n, essentially you can show that the integral goes to L in this case, okay? So what we get is that this left-hand side now is equal to 0 plus 0 plus everything in here is 0 except for L for m equal to n. So we get the integral from minus L to L of sine of m pi x over L, f of x dx equals b ml. So this implies that, and now I'll swap indices back. Bn is equal to 1 over L, integral from minus L up to L, of sine of n pi x over L, f of x dx, okay? What was crucial for that? What was crucial was that these basis functions, we call them, or Fourier modes, or whatever you like to call them, are orthogonal to one another on the domain that we're integrating over, okay? Lastly, okay, similarly for cosine of n pi x over L, we can write down an is equal to 1 over L integral from minus L up to L of cosine n pi x over L f of x dx, okay? So the way to turn this single equation for the initial condition into infinity is to integrate it against all of the basis functions that you have, and then you extract all of the coefficients that you need in that case, okay? So you might say now, okay, well, so I have what an is, okay? This basically applies for n is from 1, 2, 3, all the natural numbers, okay? I have bn here, and I have my a0 here, which is slightly different, okay? And sometimes people will just, sort of scale things by 2 in order to get rid of that extra factor of 2. But essentially, I have a way of backing out my coefficients, okay? Now, back to the heat equation. If I go back to the heat equation, remember the situation that I had, right? First of all, the boundary conditions eliminated the cosine of n pi x over L terms. So I know immediately that in my Fourier series, a0 equals an equals 0, okay? And remember also, I just worked out the theory for x is in minus L to L. But what about in the case where I'm going from 0 to L, okay? Well, in this case, what I can do is just odd reflect f of x across 0, okay? Because sine of n pi x over L is odd, so I know that I'm going to have an odd function anyway, right? So what I'll do is I'll say, I'll have this odd reflected function f tilde, f of x, that's equal to f of x when x lives in 0 to L, okay? And minus f of minus x when x lives in minus L to 0, okay? And so therefore, okay, Bn is just going to be equal to 1 over L integral from minus L up to L of f tilde now of x sine of n pi x over L dx, okay, which is going to be equal to 1 over L from the integral from minus L to L. Wait, I already did that. No need to write that again. Okay, but sorry. So now because this is odd and this is odd, then the whole thing is going to be even, right? And I can just write the integral as from 0 to L f of x sine of n pi x over L dx, right? So I get this extra factor of 2 up here because I essentially take the reflection of the even function in there, okay? So that means the full solution is going to be u of xt is equal to the integral from n equals 1 up to infinity, bn e to the minus k n squared pi squared over L squared t sine of n pi x over L. Bn is equal to 2 over L integral from 0 to L f of x sine of n pi x over L dx. That's just me rewriting the integral from above. Okay. Okay. So what did we learn from that process? So we found that essentially we can take our initial condition and exploit the orthogonality of our eigenfunctions in order to extract these coefficients as essentially integrals against our basis functions. Okay.
Professor,
Yes.
aren't we forcing f of x to be odd? It may not actually be odd, but we force it to be odd so that we only integrate it from 0 to L, right?
We don't have any information about f of x outside of 0 to L. So we're free to make up a function that's defined on the region from minus L to L, and then use the Fourier series definition that we derive for x goes from minus to L, right? Remember, we were only given the initial condition from 0 to L, right?
Yeah, yeah, yeah,
So as long as what we're doing is legal with respect to, you know, this function that we've made up from minus L to L, and it respects the function that we have from 0 to L, we can always use odd reflection. So this is, you know, this is similar to what we've done before with odd and even reflection, you know, on like quarter plane problems. So you can kind of think of it like that. Yeah. Okay.